Alright, hi everyone. We're going to finish 7.4 now. So we did a couple of cases, but we have a few more things to consider. So the new case that we haven't considered is when we have what's called an irreducible polynomial, or in this particular case, an irreducible quadratic. So what does irreducible mean? It basically means you cannot factor it. So this polynomial, for example, it's quadratic because the degree of this polynomial is 2, and we can't factor this. Right? If you try and factor it, you're kind of forced to do, there's not many options. You put x and x here to get x squared, and you have to do plus 1 here if you want to get that, or you have to try to do minus 1. But in both of these cases, these don't give that back. It is not equal to either of these, because this is equal to x squared plus 2x plus 1, and this is x squared minus 2x plus 1. So these don't give back the original polynomial. The actual factor, the way you factor it, is you have to use imaginary numbers. So this does factor into x plus I, the imaginary number I, times x plus I. But we're not going to go there. So if it doesn't factor using real numbers, we call it an irreducible polynomial. And in particular, if it's a second degree polynomial, we call it an irreducible quadratic. Okay, so we now have to consider the cases where we have irreducible quadratics in our rational function. Okay, so let's look at an example. So we have the integral of 2x squared minus x plus 4 all over x cubed plus 4x. Okay, so step 1 is we always had to make sure that the degree of the bottom is larger than the degree of the top, which in this case it is. This is degree 3, that's degree 2, so we're good. Now, the second step was we wanted to fully factor everything if possible. Okay, so the top we're not going to look at because it won't do much for us. The bottom will pull out an x, and we'll be left with x squared plus 4. And now you can see this is an irreducible quadratic term, because you can't just like the same reason we can't factor x squared plus 1 is the same reason we can't factor x squared plus 4. You have to use imaginary numbers to do this. And if you think about this as well, when you factor a polynomial, it allows you to find the roots very easily. Like when we have this polynomial, it factors into x minus 2 and x minus 3. This tells you that the roots of this polynomial are positive 2 and positive 3. Now, if you think about what this polynomial looks like, it's a parabola shifted up 4 units. It has no roots, meaning that, yeah, it probably isn't going to factor. So that's another way of knowing that this thing is irreducible, is looking to see if it has any real roots or not. So roots that are real numbers. Okay, so we have that. So how do we deal with it when we do have an irreducible quadratic term? Is we know how to deal with x, so we'll set this equal to a over x. But now, because the bottom is of degree 2, the top needs to be of degree 1. So this is how we'll break it up, and that's the new thing. So this is degree 2, so in general the top is degree 1. So this is what we want to pay special attention to, the slight difference here. but now the process is still the same. So we multiply both sides by this guy. So, you know, you multiply both sides by x times x squared plus 4, which is fine. It cancels out over here. And now you multiply this side by the same thing. So we're left with 2x squared minus x plus 4. And then this x will cancel with that x, so we're just left with an x squared plus 4. And similarly, we're left with this for the other term. Sorry, bx plus c times the whole bx plus c times x. Okay, and now we're going to do those tricks that we normally do. So what were those tricks? So we're going to let x be 0. So if x is 0, what do we get? We get this goes to 0, that goes to 0, so you're just left with 4. And that's going to be equal to a times 0 squared plus 4, so this, plus b times 0 plus c times 0. Well, this times 0 is going to kill all of that off, which is fine. So this goes away, that's why we chose x is 0, and then this is 4, so 4a. And that immediately tells me that a is 1. So a is 1, we'll keep that in the back of our heads. Now, we can't pick anything that makes this guy go to 0, because if you pick any number and you square it, it's positive, so it's not going to go. It has to be negative to cancel out with 4. And you know, even if you try algebra, what is the x that satisfies this? Well, you would need x squared is negative 4, and x would be the square root of negative 4, which again is not a real number. So we don't have that luxury in this case. So at this stage, let's just use the fact that a is 1. So this is just 1, so we can just forget about it. And now let's expand this out. So we're kind of out of tricks in this case, or the tricks that we know so far. So this is just x squared plus 4 because it's 1 times that. That's what a was. And then if you distribute the x, this is plus bx squared plus cx. Okay, so now notice that if I have x squared plus bx squared, these two terms have an x squared next to them. That means that they have to add to give a 2, because you know there's no more x squared terms here, so the two x squared terms that do add together, they should be equal to the only x squared term here. So we can get 2x squared is equal to x squared plus bx squared. That's one equation. And similarly, you know, this is the only term with an x in it. So if this is the only term with an x in it, well, it should be, c should be chosen such that this ends up being negative x. So again, we get negative x should be equal to cx. And then last but not least is the constant. Well, this constant is 4 and that's 4, so that's good. So what this means is I have to pick the right choice of b so that when I combine it with this x squared, I get 2x squared. And I have to pick the right choice of c so that, you know, c times x becomes negative x. This one is quick. This one's quick to work out what c should be, because, you know, if you just divide both sides by x, basically, if you divide both sides by x, cancels out here, and here it will give you -1. So this tells you that -1 is equal to c. Now, to divide by x, we have to make sure that x is not 0, right? But we already took that case into account. We know that when x is 0, we get something out of that, so we're good. So yeah, you can just think about the case where x is not 0. So it's fine to divide by that. So we have c is -1. Excellent. And then in this case, what I'm going to do now is notice that if you factor out an x squared from here, you get 1 plus b, right? Because distribute this, you get x squared plus bx squared. Okay? So, which more suggestively is 1 plus b times x squared. So notice the coefficient in front of the x squared here is 1 plus b, and the coefficient in front of what it needs to be equal to is a 2, meaning we get this equation, 2 equals 1 plus b. The coefficients must be the same. And so that this immediately tells you that b is 1. So b is 1, that's what we conclude. So now we have the 3 components of what we're trying to find. Okay, so now we know that this thing, now we know that 2x squared minus x plus 4 over x times x squared plus 4 is equal to a, which is 1 over x, plus b times x, so just 1 times x, which is x, plus c minus 1 all over x squared plus 4. Okay. And remember, this was the original thing that we started with, x cubed plus 4x. So the integral of this is the same as the integral of that. Which is good. Okay, so now if we break this up into 2 pieces, we get this one we know how to do. It's just the ln of absolute value of x. Now this one may require a little bit of thought. So what we can do is we can break this down into the integral of just x over x squared plus 4 minus 1 over this. Right? If you add these or subtract these two, because they have the same denominator, this converts back right into that. So we just break this up into 2 individual pieces, meaning the integral breaks up into those 2 pieces. Okay. Now this we can do with u substitution, and this one is, remember, we knew the integral of 1 over x squared plus 1. This was the integral of tangent inverse. So the integral of this gave us tangent inverse. So we have something very similar to that. It's x squared plus 4 instead of x squared plus 1. And so we could derive this formula very quickly, but if you remember, if this changes to anything in the form of a squared, where here a would be 2, right, because this is the same as 2 squared, then all that changes here is you get a 1 over a tangent inverse of x over a. That's the difference. So x over a should be, yes. So that's the only difference. So we're going to use this formula now. So coming back up here, we get that our final answer is the ln of absolute value of x plus, now when you do u substitution here, the factor you pick up is a 2x. So this dx will turn into du over 2x, because we're going to let u be equal to this. And so these guys would cancel. So you have the integral of 1 over u, which is the ln, and this 1/2 here. So this is the 1/2 ln absolute value of u, but u was x squared plus 4. And then plus now 1 over 2, because a is 2 in our case, tangent inverse of x over 2 plus c. That's the final answer. Okay, so yeah, from now on the u substitutions I'll probably do a lot quicker because I know we've seen this so many times and these problems are very lengthy, and stopping every time to do the u substitution explicitly is just going to eat up too much time. But please ask me in class if it doesn't make sense. Trying to see. So then the other case that we get is if we have a repeated, just how we had a repeated linear factor, we can have repeated quadratic factors. So in this case, we do the same thing as with the linear case. So let me just show you what I'm talking about. So let's say we have the integral of 1 minus x plus 2x squared minus x cubed. Okay, so now in this case, if we think about it, if you FOIL all of this out, the x squared times the x squared will give you an x to the 4th, and when the x hits that, you will get an x to the 5th. So the degree down here is 5 and the degree here is 3, so we're good. We don't have to do the long division. So now let's just ignore this for a second and do algebra. So because we have a repeated irreducible quadratic factor, it's the same as the linear. So we'll do a over x, then a bx plus c over the original one, and now we'll do a dx plus e of the other guy squared. This is very similar to when we had the linear factor. You would do something over the linear factor plus another thing over the linear factor squared. Say that's what it was. So it's very similar to that. Okay, so then now let's do the same process. Multiply both sides by this. So it cancels out here. Okay, and then so we'll get 1 minus x plus 2x. So a times this will be, and then we'll have bx plus c times an x. So it'll pick up 1x and 1 power of x squared plus 1. And then in this case, we'll just pick up an x. Okay, so then now, let's let x be 0. Or I guess we can just kind of do this all in one go. So because resorting to our old trick won't help us out too much, because like we can't kill these terms off. So it won't help us out too much. So let's look at this right side. Let's expand it out. So this is a times, so x squared plus 1 times x squared plus 1 is x to the 4th plus x squared plus x squared plus 1. So when you combine this, this is 2x squared plus 1. So that's what we have here. And then this x, let's let it hit each of these. So then we get bx squared plus cx times x squared plus 1. And then plus a dx squared plus ex when the x hits that. And now let's do this on the side. So bx squared plus cx times this guy. So this times that. So this gives me an ax to the 4th. Sorry, let's do this a little after. So this gives you ax to the 4th plus 2ax squared plus a. So that gives us that. And then here, bx squared times x squared gives me bx to the 4th. This times that is bx squared, cx cubed, and then that. Okay. So we have this. So now we need to start grouping things with the same powers together, just like we did last time. Okay, so there's only one thing with an x to the 4th in it right here. See, nothing else has an x to the 4th here. Does it? So it does not. So if that's the case, let's see. Actually, let's start with the other powers here real quick. Yeah, let's look at the other powers, because this one could be a little misleading. So let's start with the linear, so x. So here's an ex. Then there's a cx. Oh, and see, that's why this doesn't have an x to the 4th. My bad, so I missed that. But let's just work on the linear. So cx and ex, those are the only linear ones. Okay, very good. So we have that cx plus ex is equal to, so what's the linear term? Is negative x. Okay? So we've taken care of that. And then also let's look at the constant. There's only one constant term, right, is a. So we immediately need to know that a should be equal to 1, the constant. So that actually tells us a immediately. A is equal to 1. So we know that. And now again, if you factor out an x here, you would get that c plus e is equal to negative x. So the coefficient on x here has to be the same as negative 1. So we know that c plus e equals negative 1. So that's one thing to keep in mind. So this doesn't immediately tell us the answer, but it's something that we could think about. And then next up is, let's look at the squared terms. So we have a bx squared and a dx squared in a 2ax squared. And that's the x squared term here. So what we also know is, and now, I'll do this maybe one more time and you can see the faster way. So we have 2ax squared plus bx squared plus dx squared equals 2x squared. Okay, again, if you pull out the x squared, what this says is these must add to 2. So what I mean by you can do this a lot quicker is you can stop writing this whole x squared business and just write the coefficients, or the sum of the coefficients. So we know that 2a, but remember a is 1, so if a is 1, this is just 2. So what we know now is that 2 plus b plus d should be equal to 2, because the coefficient here is 2. So 2 plus b plus c must be 2. Plus d. This should be d. Okay? And then if you subtract the 2 over, that means that b plus d is 0. So b plus d is 0. And so that tells you that b and d are opposites of each other. So b is negative d, or vice versa. Negative b equals d, wherever you want to toss that minus sign. So that's something that we want to keep track of. So this is something, a piece of information that's really useful. So is that. Okay, so then now those are out. So constant is out, square is out. And then the cubic terms, oh yeah, the constant here is out. So then the cubic term, there's only one, is cx cubed. So we know that, immediately we know that c should be equal to negative 1. So that helps us out here. So c is negative 1. And then now if we put that into here, using the fact that c is negative 1, this tells us that negative 1 plus e is equal to negative 1. So when you add 1 to both sides, this tells you that e is 0. So e is 0 actually. So e is 0. Excellent. Now we know that. And then this kind of served its purpose. It's gone now, so that's gone. And so the last piece of information that we have is that ax to the 4th plus bx to the 4th, well, there's no 4th power here. So that means that it should be a 0 over here. So technically you could add a 0 x to the 4th, right? Because there is no x to the 4th term. So now we know that a plus b, ax to the 4th plus bx to the 4th, must be equal to 0, x to the 4th, if you like. So when you drop the x to the 4ths, this is what we get. But we know that a is 1. So we have 1 plus b is 0. That tells us that b is negative 1. So we know that b is negative 1. And that's really good, because now we immediately know what d is. Because if b is negative 1, then I have negative 1 equals d, divide by a minus sign, and that tells you that d is positive 1. So we have all 5 of our coefficients here. Okay. So now we're in business. So we know that making sure these are right. Yes. So now we know that the original integral, or yes, the integral that we started with, that guy there, or x squared plus 1, I'm sorry, x squared plus 1 squared, there we go. This is the same as the integral of, we had a over x plus bx plus c over this plus dx plus e. Okay, so that's what we had. So then a is 1, b is negative 1, so this is negative x minus 1, because that's what c is. Meaning that we can just, well, we'll talk about that later, and then d is 1, and then e is 0, so this is just what we get. Okay, so then this first integral, super quick, is this one here, is the ln of the absolute value of x, as usual. Plus now, if we factor out a minus sign here, this turns into x plus 1, so really, you can just turn this into a minus here. Okay, so we have minus, and then drop that. So then this breaks up into two pieces. So we have minus the integral of x over x squared plus 1 over x squared plus 1. Remember that these two add back up to that. So we're splitting it up just like last time. And then this minus sign technically goes to both, so that's a minus here. And then I'll rewrite this, because I want to write this as two separate integrals, just to help us deal with it. So yes, long story. Now I see that I probably shouldn't have changed the fact that they're both minus. But yes, after some algebra we get that. And then this one I'll leave the same. Okay. This one you could do with a quick u substitution. If you let u be x squared plus 1, so this is u. Then dx will be du over 2x. So this will cancel. And so this becomes ln absolute value of u plus, so this is now the integral of just 1/2, this is the integral of 1/2 times 1 over u, right, which is 1/2 ln absolute value of u. So this is plus 1/2 ln absolute value of what was u, x squared plus 1. And then this is a tangent inverse. Remember, because this is a 1, we don't actually need to change anything, no modifications. And then this one here is, again, you could do a u substitution, is let u be x squared plus 1. So then this now will be u. Then this again will turn into du over 2x. That cancels. And now this integral is effectively the integral of 1 over u squared with a 1/2. But this is the same as u to the negative 2, which is negative 1/2 u to the negative 1. So this becomes minus 1/2 times, and u to the negative 1 is the same as 1 over u, right? So this is really like negative 1/2 times 1 over u, which is negative 1 over 2u. So this is negative 1/2 times 1 over u, but what was u? X squared plus 1. So this combines to just to that. Then plus c. Make sure that's right. Oh, sorry. This should be a minus. I dropped that. That's a minus sign there. So one small error. And then this should be an x because I just copied that. Okay, then the rest is good. So that's the case. So if you have an irreducible quadratic and it's repeated, it's kind of the same process. And hopefully that new trick for finding that coefficients becomes helpful, because the old one where you let x be something doesn't always work. But if you combine both now, you can probably do this very quickly. So it's just a nice trick to have. Okay, so then this leads us to the next section. So now we've talked about many strategies of integration, but they were all isolated. You know, the integration by parts section, if you see an integral, you're going to guess, maybe I should do integration by parts. Or trigonometric substitution section, you'd be like, oh, I should try a trigonometric substitution. So now in general, if you just get an integral handed to you, find this integral. We want to think about combining all the knowledge we have to develop, a strategy for integration. So that's exactly what this section is called. So strategy for integration. And here, some of the integrals we won't do explicitly. We'll just talk about the strategy for how to do it, and then the details, they can just be worked out later in class and stuff. So the book starts out by kind of summarizing a lot of the integrals that we've developed, like what's the integral of 1 over x, what's the integral of e to the x, and so on. So it has a nice table there, and so it kind of gives us a few steps. So step 1, it says, if you can, do some algebra or use some trig identities to simplify what you have. So step 1 of all things is just to try make some simplifications. Step 2 says try a u substitution. Try making a substitution that works. And then if that doesn't finish it immediately, it turns it into another form, then you may have to think about applying some of the other techniques we know, like integration by parts, or if the substitution didn't work, then maybe you need to classify in terms of some of the types of integrals that we developed here. So trigonometric substitution, or maybe it's like a trig type integral, the ones from 7.2, or it's a rational function, so things like that. And then the last thing is, just really try and think about more creative ways if all of these methods are exhausted. So we'll do an example and let's see what we get. So the first example is this. Okay, so you see trig functions here, though this is not in the form of the trigonometric integrals we saw in 7.2. So we can't immediately apply that strategy, but let's just apply some trig here to maybe simplify this. So this is the same as, so I'm going to write this as tangent cubed x times 1 over cosine cubed. Right, because if I combine these fractions, I get that back. And I can put anything over 1. So I just split this up into two parts. And the reason why I did that is now you can write tangent cubed as sine cubed x over cosine cubed x. Since tangent is sine over cosine. And then this 1 over cosine cubed, we'll just leave it like that. Okay, so now this combines. Okay, so this maybe doesn't look, immediately much better because you have a sine cubed and a cosine to the 6th. So that at first glance doesn't look amazing. But remember the tricks that we learned from 7.2 is anytime you have sines and cosines, we learned them being multiplied by each other. But kind of the same idea you can apply for this division. The reason why I didn't do it here is because tangent plays well with secant. Remember, and because there's not a secant here, at this rate anyways, it's not nice. We could have introduced secant into this if we wanted to. So another way of doing this was to just immediately notice that 1 over cosine cubed is a secant cubed. So maybe these are both worth noting, is that we could convert our original integral into these. Both of these are completely fine. Now it's up to you which method you want to choose. With this method, you would want to write this sine cubed as a sine squared times sine, and then convert one of these sine squareds into 1 minus cosine squared. And then make the substitution u is equal to cosine x. And that would let you finish out this problem if you did it this way. Now for this one here, because there's not an even power of secant, we'll convert this into a tangent x times a secant x here. So I pulled one tangent and one secant away here. So I'm left with a tangent squared times a secant squared. And then this tangent squared you can turn into, remember, 1 plus tangent squared was secant squared. So tangent squared is secant squared minus 1. So you can convert that tangent squared into that. And then now at this stage, you can make the substitution u is secant. Because the derivative of secant is secant tangent, it'll kill that off and you'll just be left with u's. So these are two different ways of approaching this problem. So see, at this stage, there's more than one way to do this. Okay, so then next is, let's say we have this integral. And then, so we have integral of e to the root x. And this is getting very faint, so maybe we'll just, I should write with a green. So let's say we have integral of e to the root x. Okay, so think about it. U substitution will not help us in this case, because if you let u be root x, then du is 1 over 2 root x. So at least u substitution won't help immediately. Let me say that. And then you would get 2 root x du is dx. So then this guy would turn into the integral of e to the u times 2 u du. Okay. Because, or let me write this out in a little more detail. So this integral will turn into the integral of e to the u, and then dx will turn into 2 root x du. And then I'll pull the 2 out in front. And then I'm going to change root x into what it originally is u. So this is now u e to the u du. Now you may say, that just made things more complicated, which it does look more complicated, but we can take this integral. You can use integration by parts here. You can do this by integration by parts. Because integration by parts uses u and v already, let's maybe use m instead here. So the variable m will get used. So this is m e to the m dm. And you could use integration by parts now, because you can let u be equal to m, so du is dm, and you can let dv be equal to e to the m, so v, which is the integral of this, is e to the m. And this will transform into 2 times, so remember it's uv minus the integral of v du. So it'll be uv m e to the m minus the integral of v du e to the m dm. And the integral of e to the m is just itself. So this is actually that. And then when you distribute the 2, this becomes a 2, that becomes a 2. And then all you have to do now is substitute back the root x. So your final answer is 2 root x e to the root x minus 2 e to the root x. So notice how we did a substitution and an integration by parts here. So this is you can see how now all these techniques can kind of come together into one. So let's keep pushing on. Then the next example is this guy. Which after, about 20 minutes ago, that we saw this a lot. This will be done by by partial fractions. But first, notice that's a 5th power, this is a 3rd power. You have to do long division and then do partial fractions. So long division, then partial fractions. Okay. Does that make sense? So again, just from the form of this, our mind immediately needs to think, probably the first step would be partial fractions. Any other technique like u substitution, integration by parts seems a little out of place with this. And then here is one where things are very interesting here. So say we have this. So if we let u be equal to this, then things will work out, but it'll be extremely complicated. It won't be very nice. It'll be kind of nasty. Because let's think about it. Like, you know, if you take the derivative of this will be equal to 1/2, because this is this to the 1/2 power. So 1/2 this guy to the negative 1/2 times now the derivative of this guy, which this is already pretty nasty. So the derivative of this is not the best thing ever in the world, and so you can see how this guy will start to lead to kind of a very bulky expression. So another way of doing this actually is to do a little bit of algebra, is to actually multiply the top and bottom by what's essentially the number 1, but it just looks, it's in a very nice form. So if you multiply the top and bottom by that, this turns into, now remember, if you have two square roots multiplying each other, this square root we can write like that, because the square root of a over root b is this. Meaning if you have a square root over a fraction, you can take the square root of the top and the bottom. And then the other thing we're going to use is this. So if you have two things multiplying under a square root, you can put their product under one common square root. So in this case, this becomes the square root squared, right? I mean, this times itself is squared, so we can immediately see that this one just goes away. Square root and square undo each other. And then up top, when you FOIL this out, this is the integral. This becomes 1 minus x squared. Like that. Oh. Now actually, when I look at this, the better way to do this would be the opposite. So make this 1 minus x instead. You know, we have free reign to do whatever we want because it's the number 1. So instead, up top, we'll get something times itself is squared, take the square root, and undoes that. So this will be 1 minus x. And down here, this will be the 1 minus x squared. Why is this nicer? Well, again, you can break this down into two pieces. So each of these can get their own integral. This one is a very famous integral. It's the integral, I believe, sine inverse, yes. This is just sine inverse. And now this one you can do with the substitution u is 1 minus x squared. Because then du over negative 2x will end up being dx. So they'll cancel here. And this will be so 1 over root u. You can rewrite that as u to the negative 1/2. And then so this is, so you add 1 to this and divide by that same thing. So u to the negative 1/2 plus 1 over that. is u to the 1/2 divided by 1/2, which is 2 times the square root of u. Because dividing by 1/2 flips this up as a 2, and u to the 1/2 is root u. So this is just minus 2 root u, but what was u? 1 minus x squared. And then, oh, there was this 1/2 here. So sorry, this negative and that negative cancel here. So this becomes a plus. And this 1/2 here hits that 2 to actually kill it. So this is actually the final answer. So yeah, some things canceled out. Okay, so sorry, I'm trying to do these integrals a little quickly just to show you the different ideas and strategies that you might see. So yeah, at this point it takes a little bit of, you definitely want to go through the checklist, think about stuff, but this is kind of like a puzzle. There's no one way to do it, and there's no like absolute way to do this. That's what kind of makes integration interesting. It's a little mental puzzle that you kind of have to think about, and it's kind of like an art form, so it's a little bit of fun if you think about it in that positive way. And then the last question becomes, which is a good question to ask, is, so I'm getting close to the end of Calculus 2, which was about integrals. Can I take the integral of every single function now with the known techniques that we have? And the answer is no. For example, unfortunately, it's no. So for example, if you want to find the integral of this guy, none of the techniques that we have can deal with this integral, which kind of sucks, like I wish I could take this integral. But yeah, at this point, a function of this form, we don't know how to take its integral. We'll have to develop some more sophisticated ideas about functions to be able to deal with this. And that's in the next calculus course. So the idea is that you can write this function here as a sum of an infinite amount of other functions. You can write this whole thing as a very long polynomial. So what you'll learn in calculus 3 is that you can write e to the x as 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24, where these numbers, another way of writing them is, this is the same as the number 2 factorial. You'll learn about this a little later. 3 factorial, 4 factorial. Notice that corresponds to the power, and so on. And then so e to the x squared would just be 1 plus, you replace each x with the x squared. So this would be x squared plus x to the 4th over 2 plus x to the 6th over 6 plus x to the 8th over 24, and so on. And then to take the integral of this, you'll take the integral of each piece now. Because these are equal, you'll take the integral of each of these pieces, and that can tell you the answer. So that's what I meant by a little more sophisticated stuff. Now, this already has a lot of theoretical considerations that you have to make sure are okay, but this is just the idea. So the answer is no, we cannot integrate every function at this point, but we can integrate a very, very good amount of them. So, of the functions that we can integrate, not every function you can take the integral of, but of those that we can, we have a pretty good grasp of them now. So that's pretty cool that we've gotten to this point. So the last thing we'll talk about in terms of integrals is what is known as the improper integrals, which are integrals where the area under the curve may be infinite. And so sometimes it is infinite and sometimes it actually is finite. But we'll talk about that next time. Okay, see you guys later.